One of the oldest and most widespread diseases in the world, cancer has always existed and is found in all living things, including plants. It was once thought to be related to the humours, to be contagious or viral in origin. Today it is believed that the cause may be genetic. In every age, new weapons have been unsheathed against cancer, but none have succeeded in vanquishing it. And yet scientists are now able to decipher some of its most intricate processes. Could these advances have been misleading? Could they have in fact led the scientific community astray?
It now appears very likely that we got lost in the details. Our focus was wrong. We were looking at the details of the engine in the car when that wasn't really the problem.
We tend to research the details without seeing the big picture. We lose the forest for the trees.
Einstein said for an idea that people don't think is crazy in the beginning, there is no hope.
Time has come in America when the same kind of concentrated effort that split the atom and took man to the moon should be turned toward conquering this dread disease.
It's now been over 40 years since the war against cancer was declared by one government or another.
Le cancer ne sera pas vaincu en un jour, mais un jour il le sera.
Today I'm announcing we are directing $30 million of that new budget.
Since then, real progress has been made. We are now able to detect, treat and prevent cancer much better than in the past.
La lutte contre le cancer s'est fixée comme objectif.
70% of the cancers that were fatal in the 1950s can now be cured. But such undeniable achievements are, in the end, relatively minimal. In spite of the many billions that have been invested in cancer research in the last half-century, mortality rates have not decreased as much as expected. The disease continues to kill 8 million people every year. But how well do we really know this enemy? And to begin with, how do we define it?
Cancer is the dangerous overproliferation of certain cells in the body. When everything interacts in a harmonious way, the body grows. That's what happens in children or in fetal development. When cells multiply in what we call a normal way, the process is harmonious and coordinated. But when the cell proliferation does not respect this process and gets out of line, so to speak, that's what we call cancer.
I mean, you have to remember what cancer is. Cancer is a kind of traitorous cell in your own body, and that's one of the things that makes it so diabolical, so difficult to treat. It's your own flesh and blood that has become immortal. The cancer cell is an immortal cell. People don't realize this, but all of our cells are destined to die, and it's actually the death of the cell that's healthy. Our cells regenerate through death. They're constantly growing. But if a cell stays alive and keeps growing, that is what cancer is.
Where does this paradoxical explosion of life that is cancer come from? How can it be prevented and controlled? Surgery was first used to treat cancer in the 19th century, and then, at the beginning of the 20th century, radiation therapy was developed. Both methods target the tumor, which is a cluster of cancer cells that form in an organ. But these methods do not prevent some of the cells from escaping and spreading to other organs. The resulting secondary tumors, called metastases, are often highly malignant. In order to stop this fatal process, a new weapon was developed in the 1950s. On December 2, 1943, German warplanes bombed the town of Bari in Italy. One of the ships in the harbour exploded. It was carrying 2,000 bombs of mustard gas, a highly toxic poison gas. Over the next few months, more than 1,000 people died, both soldiers as well as civilians. The doctors who treated the victims poisoned by the gas noticed that they had very few white blood cells in their blood. This incident led researchers to come up with a new idea. If mustard gas could kill blood cells, why not use similar toxic chemicals to eliminate cancer cells? That was the beginning of chemotherapy. A few years later, it was being used effectively against previously incurable cancers. However, chemotherapy hits hard and indiscriminately. It kills diseased cells as well as healthy cells. It is a scorched earth strategy applied to the entire organism that is extremely harsh on the body. Its side effects range from nausea to hair loss, to anemia and other immune system disorders. Moreover, while some cancers respond to it, others resist it, for reasons that we're still unable to explain.
The idea of using chemotherapy against cancer was purely pragmatic. We don't know why a particular tumor responds specifically to such and such an agent. However, what we suspected was that chemotherapy acted and could be especially effective on rapidly proliferating cells. That's why pediatric tumors were good targets. But unfortunately, this explanation turns out to be insufficient. So we have made advances, but we do not necessarily understand why we made those advances.
While cancer treatment has progressed significantly, many grey areas remain with regard to the disease itself. In the 1970s, it was thought that the mystery had finally been pierced. Two researchers, Harold Varmus and Michael Bishop, demonstrated for the first time that the enemy might come from within our own cells. It could even be lurking in our genes. For this discovery, they were awarded the Nobel Prize. In order to understand this, we must return to the basic principles of the science of genetics. They postulate that DNA controls everything in our bodies. Cancer occurs when something disrupts the codes that regulate the way everything functions in the body. A gene that is damaged, broken, or undergoes mutation may cause cells to deviate from their genetic programming.
When certain cells start to go out of control, which is the case with cancer, they are no longer following their genetic programming. What happens in this process, which is called mutation, is that the cells change their own DNA. So the DNA is altered, the control mechanism is impaired, and as a result, they escape genetic regulation. That's what is now called the genetic theory, or the mutational theory of cancer, which states that cancer is caused by mutations that occur in cancer cells.
A new era was dawning. Researchers began using new techniques to hunt for oncogenes, those genes whose mutations are the cause of cancer. Robert Weinberg is an iconic figure in the field of cancer genetics. Following in the footsteps of Varmus and Bishop, his work has helped to greatly elucidate the biological factors at work in the development of cancer.
In 1978, we began an experimental procedure that allowed us to demonstrate a year later that, in fact, if one looks into the DNA of cancer cells, one can find their damaged genetic information that is responsible for driving the unconfined, the unconstrained proliferation of human cancer cells. The DNA that we looked at there turned out to be a cancer-causing gene, which is called an oncogene. The oncogene is a damaged form of a gene that resides in normal human DNA, and under the influence of the chemical carcinogen, this gene is mutated, it's altered, so that its altered sequence information now creates an oncogene that persuades the cell to grow without limit, without any confinement, and to grow and form thousands, millions, billions of descendants.
Vast amounts of human and financial resources are thus being poured into the area of oncogene research. Billions are being invested in equipment and technology. The human genome is being mapped, and we will soon know everything there is to know, not only about cancer, but about many other diseases as well. The genetic approach now stands out as the one and only path.
I do think that there is, by now, a commitment to genetics. There is a commitment in our National Institutes of Health. How could there not be? Our director is a geneticist. We have by now an enormous infrastructure of biotech companies built over the last 50 years to work with laboratory scientists to study the genetics of this and the genetics of that.
Today, we have dozens of countries across the world really involved in the race to actually sequence cancer genomes, find cancer genomes. So the science of cancer is really progressed very quickly because we now understand genetics and genomes, and we can actually catalog mutations.
Canadian scientist Thomas Hudson runs a large international consortium that is in the process of completing the sequencing of 25,000 tumors.
Our ability to not just discover cancer genes, but rapidly understanding the biology of the cancer genes, and try to make drugs for the most important ones, is actually becoming almost routine.
When I was studying the rise of oncogene research, it was a new bright star, right? It was a hope. People really thought that we were getting to the cause, the basic causes of cancer, and that it would eventually lead to solutions, to treatments.
In the late 1990s, drugs designed to target and affect the behavior of cancer-causing genes were developed. Next to chemotherapy, these so-called targeted treatments appear to be considerably less destructive. Their impact on the body is gentler, with fewer side effects. The pharmaceutical industry has invested massively in these new therapies, which represent more than half of the anti-cancer drugs now being developed. 200 products are already on the market, and 900 are in preparation.
There are a lot of advances happening in oncology today because of targeted therapies. And we know that some, like Gleevec, actually have a long response. But the disappointment is many of the new targeted therapies don't last as long. And so there's limitations in terms of their effectiveness for patients. It could be 3 months, a year. But very often the disease comes back and can overcome that resistance.
Drugs such as Gleevec and Herceptin have without question contributed to advances in the treatment of certain leukemias and breast cancers. But for almost all of the other cancers, the results have been disappointing.
In principle and logically, targeted therapy is much more promising. The unfortunate outcome, however, is that targeted therapy often works brilliantly, but after 6 or 7 or 8 months, the cancer cells figure out a new way to start proliferating, and these newly formed cancer cells are no longer affected by the initially introduced drug.
It means that we would become caught up in a never-ending chain of events without ever really arriving at a cure. That, I think, is one of the limitations of targeted therapies.
Why is it taking so long for the genetic revolution to come up with effective treatments? It is now estimated that over 2,000 genes might be involved in various cancers, and that the mutation rate could be 1,000 times higher depending on the tumor. And the further we probe, the more complicated it gets.
The major challenge that we have is to understanding what the data means. I was part of the Human Genome Project during the 1990s, and we sequenced that whole genome. It took 10 years, and we still don't understand most of the genes and the proteins and what the genomes do. So we still, our fundamental our ability to do an interpretation of one genome, a whole community of scientists across the world is still challenged. It's how difficult it is.
The information, the technology for analyzing cancer cells is now so powerful that we are being inundated, we are being flooded with large amounts of information that vastly exceed our capabilities of digesting the information and understanding its implications. Clearly, without understanding what makes cancer cells grow abnormally, our hands are tied in terms of being able to create new kinds of therapies.
There are people who cynically would say, if you have a hammer, every problem is a nail. Cancer genes are now the nails because we have molecular genetic tools, we can go and hammer on cancer genes. So the question of, is this the best way to study cancer? Was it the best way? It was, in a certain sense, the best way given the tools that people had. Was it the solution to the problem of cancer?
In the early 1990s, patient advocacy groups were formed in protest against this fixation on genetics. They criticized its lack of therapeutic results. The organization Breast Cancer Action was founded in San Francisco in order to get cancer research out of its rut by challenging, first of all, its dogmatic focus on genetics. Yes, inherited gene mutations may increase the risk of cancer, but only in 5 to 10% of the cases.
When I was diagnosed, that there was a way in which the doctor just wanted to take what he had in front of him. That's to say, you know, a 36-year-old person with this stage breast cancer, and therefore they need this treatment, and throw me into the numbers.
I had a really smart doctor say, well, you don't have a family history. And they said, well, you can't have breast cancer. And I, oh, okay, and I nodded along, but I did have breast cancer, and I was, had done all those things you were supposed to do, and I felt like it was a revolution for me to find out the things I found out.
Inheriting a gene does not mean that you will get breast cancer, and we really do have to look at the inherited gene and environment interactions and why for some people it leads to cancer and for some people it doesn't.
But I think in the last 10 or 15 years, there's been so much concentration on genetics, and I see it in other diseases where they've accounted for the incidence of these various diseases because of genes that they've identified that people have in common. I don't know how that affects breast cancer, but I know that in general that this investment that genetics explains everything has kind of put things off track.
Could the scientific community have been on the wrong track for the last 30 years? Have we in fact come to a dead end?
By looking at these details, it looks as if we lost the forest for the trees, as Americans would say. And the holistic view became less prominent.
Back in the 1970s, research by American biologist Mina Bissell tended to prove that cancer arises from an interaction between certain cells and their environment. She was one of the first scientists to challenge the genetic theory of cancer.
When you take these cells from the person and put it in a dish, or from an animal and put it in the dish, the genes are not fixed. They are regulated by context. They are regulated by microenvironment. So that just clarified a lot of things for me, that again, context or microenvironment, and in this case, the architecture of the tissue was very, very important. And once you destroyed the architecture, that in combination with the oncogene could make a tumor.
But at the time, the budding sphere of genetics was monopolizing all of the attention, and Mina Bissell's work was virtually ignored.
People say Mina is a pioneer. They say she's a visionary. Some people say. Some people think I'm crazy still. But no, I didn't think I never thought. I just was curious. We published the papers in very many good journals, and the reactions basically were disbelief, or nobody paid attention. People would not quote them. They would not say this. It's only in the last 10 years or so that a lot of very well-known people are aware of the work, and they quote it, and they also say it's pretty obvious.
In order to understand cancer, do we need to change our focus? Should we examine cells in interaction with their environment? Consider how they breathe, eat, and develop? Observe them like we would observe an animal or a plant living within an ecosystem.
In a forest, if there's a plant or an animal species that proliferates to the point of destroying the ecosystem, that is literally the equivalent of cancer in the body. Rather than seeing the body as something that functions under the centralized control of our DNA, if we see it as a self-regulating system, like a forest or an ocean, we will then start to look at how the element that is proliferating gets access to nutritional resources, and we'll study the predators. So, for example, if a certain type of rabbit suddenly begins to multiply to the point of destroying the forest, we're not going to say, oh, the rabbit has mutated. We would wonder instead if carrots hadn't become more abundant for some reason, or if some of the other species that would normally compete with the rabbits hadn't disappeared, or whether the foxes that kept the check on the rabbit population hadn't some kind of problem that year. And so all of a sudden, instead of looking for mutations, you're faced with a more global vision of balances and imbalances.
Cancer specialist Laurent Schwartz also supports a more global vision of the cancer process. If we want to better understand how a cancer cell thrives, we have to study its resources and how it uses them. That is what we call metabolism.
A cell is a living organism. If you take a small human cell, remove it and put it in the right environment, one that provides it with water, blood, and whatever it needs, it will grow. It'll take in food, digest it, and continue to survive, and it will use genes, enzymes, and so forth in order to do so. It's the same with a cancer cell. It takes in food, it grows, and it uses enzymes. It's clear that in order to divide, a cell has to grow. It may be stating the obvious, but if you don't eat, you won't grow. And if you burn everything off when you're out jogging in the morning, you'll never get fat. So if you want to get fat, you have to take in food and not burn it off. And that takes us back to the hypotheses of the 1920s, which show quite simply that cancer feeds on glucose, in other words on sugar, in massive quantities that it cannot burn, and so it grows. And when it grows, the cells divide, and when they divide, they become hard. As every clinician knows, cancer is hard to the touch. And then, when it's under pressure, metastatic cells will start to break off.
This theory of cancer based on cell metabolism has already been postulated back in the 1920s by the German biologist and Nobel laureate Otto Warburg.
Alle Krebszellen, welches auch die entfernten Krebsursachen sein mögen, sind ausnahmslos als gärende Körperzellen erkannt worden, die also die letzte und allgemeine Ursache des Krebses sind.
Otto Warburg believed that metabolism plays a key role in the development of cancer. It is concerned with the way in which our cells feed, the way in which they do or do not digest the sugar, fat and proteins they absorb. A normal cell takes in, for example, glucose, which is broken down during a first phase and then converted by the mitochondria, which are like the lungs of the cell. In order to do this, oxygen is used. If everything is functioning normally, nutrients are burnt and converted into energy. A cancer cell, however, behaves as if it were deprived of oxygen. Without oxygen, it is unable to burn the glucose, and so very little energy is produced. To compensate for this, it consumes huge amounts of glucose, which is still unable to digest. And this, in turn, leads to a process of fermentation and continuous cell division. This is what is called the Warburg effect.
Wäre es meines Erachtens an der Zeit, Maßnahmen zur Verhütung einer Krankheit zu ergreifen, an der jährlich viele Millionen Menschen sterben.
Otto Warburg was awarded the Nobel Prize for his work, but his theories subsequently fell into oblivion. During the war, he was protected by Hitler, who had a well-known phobia of cancer, and so, for historical reasons, he was made to pay for his pact with the devil. And then the rise of genetics, which dominated the research and drained all the funds, took care of the rest. In the last 10 years, however, there's been renewed interest in Otto Warburg's theories. cancer cells and their metabolism are once again being investigated around the world. In January 2014, a conference on metabolism was held in Luxembourg for the first time ever in Europe. Scientists from around the world came to discuss their work, galvanized by this exciting new possibility for cancer research. Many of them now believe metabolism to be the Achilles heel of cancer cells for any type of cancer.
People like me have argued, instead of looking at all of these changes all the time, the genetic changes and all this bioinformatic analysis and the constant need to sequence, and maybe we should just step back and look at some other ways to think about cancer. We had plenty of in vitro data that if you disrupted...
The American researcher Navdeep Chandal first became interested in metabolism while he was a student back in the late 1990s. He felt it was a subject that deserved much more attention than it was getting, at a time when everyone else was focusing on genetics.
So in other words, cancer metabolism is an alternative, because now you're not looking at genes, you're looking at metabolic pathways. And by the way, we know those pathways. We've known those pathways for 50 years. So now you don't have to go in and rediscover anything new. I mean, there is some new pathways still yet to be discovered, some small new pathways, but generally that encyclopedia of pathways is there. And now we just have to go back and look at those pathways, how they're being rewired in cancer. Because those pathways make much better targets than anything in the nucleus, I would argue. That's a biased opinion.
If genetic mutations are not the primary, but rather the secondary agents of cancer, then what causes the disease? And in order to fight it or prevent it, where should we focus our efforts? What kinds of strategies should we employ?
Obesity is the worst risk factor for cancer. One of the things I say to people, I say reduce the sugar intake. Sugar intake, metabolism works in conjunction with a whole lot of other things, and it works in conjunction with obesity. And the worst thing that, for example, has happened in US, there is this huge amount of obesity because people eat, their food is not what our body needs. So, in fact, we could reduce the amount of cancer in the world by a huge amount if people would have more fiber, less sugar, less bad fat.
So is cancer just a question of diet? That would be too simple. To begin with, the foods we eat are not the only things that nourish our cells. There are other factors involved in cellular metabolism.
For adult cancers, you very often have an inflammatory stage. For example, alcoholism will give you hepatitis, an enlarged liver, cirrhosis, and then liver cancer. For a chronic smoker, you'd get chronic bronchitis, coughing, and then lung cancer. So we find this sequence almost all of the time: inflammation, fibrosis, cancer. Inflammation is a change in metabolism that occurs when a cell is confronted with a violent and massive absorption of food. The cell doesn't take it very well, and very often when it happens, some of the cells will die. The cells that survive find themselves gorged with food, and they will change their behavior and start to proliferate.
Metabolism is a great sensor in changes. It can detect changes in diet, environment, and even some like your habits. If you have the same sort of genes that you've had for 10,000 years, and what's changing is diet, environment, and habits, the first thing that's going to sense those changes in diet, or your environment, or in your habits even, is metabolism, which then feeds onto the genes, and then the genes drive the disease. That's the new paradigm.
A new paradigm also means new therapies. In what ways can we act on the metabolism of cancer cells? How can we stop them from proliferating? What treatments can be used?
There are various ways of changing tumor metabolism, of improving it. You can do it through your diet, in other words, by reducing the amount of glucose that you consume, and by reducing the amount of food that you eat in general. That's one possibility. However, it hasn't really been tested. Many people do it, but to be honest, we have very few of the proper, clear-cut kind of studies that scientists are so fond of. Another way is to work with the kinds of drugs that specifically target those circuits. That's the approach we've chosen because it's easier to study.
Professor Navdeep Chandal is convinced that certain agents that already exist, that are already being prescribed for other ailments, could also be effective for treating cancer. In fact, there are already an estimated 100 drugs that could be used due to their action on the cellular breakdown of glucose.
In the last 15 years plus, the epidemiologists, just looking at records, noticed that people who were on metformin had lower incidence of cancer. And so that prompted people in the laboratory to test metformin as an anti-cancer agent in mice. And they found, in fact, mice, we use that as we use it in the laboratory as our model for cancer, that a variety of different cancers, colon cancer, lung cancer, pancreatic cancer, if you gave mice metformin, you had lower cancer. So that was good.
Metformin is an anti-diabetic drug that has been on the market since the late 1960s. How could it contribute to combating cancer? Its primary action is to inhibit glucose production by the liver, and we know that cancer cells are avid consumers of glucose. Metformin would thus be able to cut off their food supply, which would in turn prevent the diseased cells from proliferating.
We did it in 10 mice, and metformin decreased tumor burden by 75%. Obviously, it's not meaningless. It can slow the progression down. Maybe you don't cure it, right? But it can increase the longevity.
There are limitations, though, of the work done in petri dishes and in animals. And in relation to metformin, one of the major concerns is that much of the work has used metformin in concentrations that are unsafe in humans. So it's very difficult to translate much of that work into the clinical setting.
And yet, the Canadian researcher Pamela Goodwin has decided to take up the challenge. She's currently overseeing a clinical trial being carried out in Canada, the United States and Switzerland. It involved 3,600 breast cancer patients who have since 2013 been taking 2 metformin pills per day in addition to their standard treatment. The results will be evaluated in 2017.
The goal of this study is to see whether adding metformin to standard treatment of breast cancer will improve the survival of women with breast cancer.
Every year, over 1 million women around the world are diagnosed with breast cancer, and nearly half of them will die from the disease. Yet testing an old medication like metformin, which might prove to be effective, was an uphill battle. It took 10 years for Pamela Goodwin to obtain the funds needed for this study.
When scientists like myself and others that are interested in metformin want to develop an available drug as a cancer treatment, it's very difficult. Many other scientists that are looking at other agents have faced challenges and haven't been able to do the definitive studies. And I think we as a society have to address this issue. If metformin proves to be effective in breast cancer, we estimate that first it will cost about $200 a patient for the entire 5 years of study. That is very inexpensive compared to the $50,000, $75,000, $100,000 that it costs for some of the new biologic treatments. But more importantly, it's a drug that can be used around the world. It's low cost and low toxicity, and it's oral, it's a pill. For better or for worse, much of the drug development research that's done in cancer is done by pharmaceutical companies. And these companies are making major contributions to cancer. But they're focusing on drugs that have come through their pipelines for which they want to make a profit.
Several giants in the pharmaceutical industry, sensing the potential for a new market, are now working to develop metabolic treatments for cancer.
When we started the company in 2002, and again it was based on targeting this unique metabolic properties of cancer cells, we were probably one of maybe 20 or 40 people that we spoke with who were even aware of Otto Warburg. And occasionally we would meet with potential investors who were older, guys in their 60s and 70s, who when we described what we were doing, they would say, "Oh, you're targeting the Warburg effect."
In the United States, certain companies are already entirely devoted to the metabolic approach. Among them, Threshold Pharmaceuticals, based in South San Francisco, California.
The idea is that if you can develop an effective therapy that really targets the Warburg effect, you may have a much broader therapeutic that would treat a much wider variety of cancers than would be the case with these molecularly targeted approaches.
Threshold Pharmaceuticals is testing a new drug called TH302 in several countries. In Germany, oncologist Peter Hohenberger is using it on 10 patients who have advanced stage cancer with disseminated tumors. The aim of the trial is to evaluate the effectiveness of combining TH302 with other treatments.
Phase 2-Studie oder beginnende Phase 3-Studie mit einem neuen Medikament, das heißt TH302. Es ist eine Therapie, wo mit einem speziellen Molekül, das sich erst im Tumor eigentlich seine Aktivität entfaltet, dagegen den Tumor vorgegangen wird.
Also das heißt, es wirkt dann sehr lokal, wenn ich das jetzt richtig verstehe, oder?
Ja, soweit wir es im Moment wissen, wirkt es im Wesentlichen lokal. Es wird dort, wo der Tumor spezielle Stoffwechselcharakteristik hat, aktiviert sich dieses Medikament. Was man haben möchte im Rahmen von Therapiestudien ist...
In a therapeutic study, what we want to find out is how effective the treatment is.
Dazu ist der eine Aspekt, ist, dass die Tumoren...
This can be measured by the fact that the tumors are shrinking, and so that's a positive sign. Our primary goal, however, is to extend the life of our patients.
Zu gewinnen.
Wie lange würde dann diese medikamentöse Therapie erfolgen?
Typischerweise würde man sie etwa 6 Wochen vorbehandeln, bis man braucht eine gewisse Zeit, um auch abschätzen zu können, wie lange es dauert, bis der Tumor seine Stoffwechselcharakteristik verändert. Aber das ist jetzt so das erste Mal, wo man richtig breit in unbehandelte oder in nicht weit vorbehandelte Patienten geht.
Okay, und mit welchen Nebenwirkungen muss man dann rechnen oder muss ich rechnen?
Also Sie können rechnen mit Auswirkungen auf das Knochenmark, dass zum Beispiel die weißen Blutkörperchen nicht so gut funktionieren oder die Zahl der weißen Blutkörperchen abnimmt. Es kann sein, dass die Blutplättchenzahl abnimmt. Typischerweise ist am Anfang der Behandlung wenig Nebenwirkung. Im Lauf der Zeit, das heißt, wenn das Medikament kumuliert, ist das Risiko eher höher.
Ja gut, nimmt das zu, ja, das kann man nachvollziehen. Okay.
Das dauert lange.
Of course, it takes a long time to develop a drug that we can then prescribe for our patients.
Das ist oft ein Prozess, der sich über 4-5 Jahre...
It's a process that often takes 4 or 5 years. Before we can use a drug, all of the relevant studies have to be conducted in order to prove that it actually offers something more. For our patients, of course, the procedure is too long.
Natürlich zu lange.
Since it takes such a long time to get a new drug out and onto the market, many patients will never get the opportunity to try a new treatment, even if it has a good chance of prolonging their lives.
The time frame for conventional or standardized clinical trials does not match the time frame of someone diagnosed with cancer, who is in a hurry, and that's understandable.
Et ça se comprend. Si je veux m'en sortir, il faut que je casse mon schéma de vie. Mon schéma de vie, c'est mon schéma alimentaire, c'est mon schéma de pensée, mon schéma relationnel. Et il n'y a que comme ça que j'ai une chance de m'en sortir.
Qu'est-ce qu'ils vous ont dit sur le pronostic et tout ça? Qu'est-ce que vous cherchez?
Moi, ce que je cherche, c'est la guérison. Je sais que c'est la guerre, quoi. Donc, pour moi, Ils m'ont dit, on va vous faire un traitement d'abord 3 mois, on va voir. Donc je leur ai demandé les chances. Donc le médecin m'a dit 30% de chances que la tumeur régresse, 30% de chances qu'elle se stabilise, 30% de chances que ce soit inefficace.
Since 2009, Dr. Lauren Schwartz has been advocating the idea that a combination of drugs, including metformin, which is already on the market for other diseases, could act on cell metabolism. Tests carried out on mice have indeed been very encouraging. Such drugs are inexpensive, their side effects are already known, and combining them makes them more effective.
Ça permet de rentrer dans la mitochondrie, de rouvrir la porte pour être brûlé.
However, in spite of his repeated requests, he has been unable to obtain the authorization and the funding needed to conduct clinical trials on patients.
Everything we've done has been published. We've had numerous articles in well-known international reviews. And yet there has been absolutely no response. It got to the point that I decided I had to write a book about what I was thinking. And that's when the patients started coming to me. And since those who contacted me knew they had very little time left, I felt I had to inform them of what I thought had a chance of helping them.
Quand on t'a annoncé la maladie, comment ça s'est passé? Comment t'as réagi? Qu'est-ce que ça t'a fait?
Eh bien, d'abord, on a...
Some of the members of the association Facing Cancer Together in the French city of Nantes have decided to try this experimental treatment.
Et quand je suis revenu chez moi, j'ai dit à ma femme, mais dans 15 jours, je ne serai plus là, parce que c'est pas possible.
The trials we've conducted come under the heading of compassionate use. Physicians are torn between 2 obligations, between 2 laws. On the one hand, trials that are extremely regulated, and on the other, assisting a person in danger. We're authorized to prescribe treatment when it concerns people who are in danger.
Mon expérience à moi, c'est que moi, je suis dans le cancer depuis 14 ans, j'ai 5 récidives, j'ai eu, vous le savez bien, 6 opérations, j'ai subi 2 fois de la radiothérapie, c'est-à-dire 2 fois plus que la dose légalement permise, j'ai plus le droit d'en avoir. Les chimiothérapies, j'ai eu 3 fois des parcours plus ou moins longs de chimiothérapie, je suis devenu résistant un peu à tout, la dernière fois, ça m'a fusillé, je suis rentré ici pour mourir à mi-traitement, quoi. Puis vous me voyez aujourd'hui, je peux faire le clown, hein. je peux encore faire le clown, hein. Eh bien, au bout de le 8 janvier, c'est-à-dire au bout de 8 jours du protocole Schwartz, le marqueur ACE du cancer s'était cassé la figure. Voilà voilà les copains, les copines, ce que je voulais vous montrer. Là, ça a commencé à monter, puis ici, ça s'est accéléré, la remontée. Et là, j'ai fait intervenir la molécule supplémentaire du docteur Schwartz. La troisième. Et la 3e molécule que j'ai mis là, tac, mon truc est reparti à la descente. Cette analyse-là est d'avant-hier, lundi soir.
C'est vrai, bon, moi je vais pas faire voir mes graphiques qui sont à peu près la même chose que toi. C'est-à-dire que bon, j'avais un marqueur qui montait régulièrement. Puis dès l'instant que j'ai commencé à prendre son traitement, ben, ça s'est mis à replonger, quoi. Et donc maintenant, mon marqueur, pour l'instant, se stabilise à la limite haute de la normale. Ce qui me fait dire des fois que je suis guéri, quoi. Puisque je suis dans la norme à un moment. Bon, c'est pour histoire de... Voilà. Et pour moi, c'est vrai que ça a été une ouverture parce que je supportais de plus en plus mal aussi les chimios, quoi. Elles me déglinguaient complètement, quoi.
Is the treatment prescribed by Dr. Schwartz the miracle we've all been waiting for? He himself refrains from drawing conclusions with regard to a possible or permanent cure.
So far, we've treated, both myself and other people, over 100 patients. And several articles have been published that suggest, and I think the term suggest is the appropriate term, that suggest that we are able to slow down the progression of the disease. In certain cases, we've seen a decrease in the number of tumor markers. Other cases could be called miracles. In the majority of cases, unfortunately, the effect is temporary, and I don't understand why it's only temporary. In other words, they improve and then afterwards they relapse. But even if we were able to make just a tiny breakthrough, it may not be enough for the patients under my care, but it's still pretty good. Of course, what's also important is to take what we already have, which is far from being perfect, and try to improve it. Combining it with chemotherapy would probably be a good thing, and it's likely there are other agents that could be introduced. At any rate, it's quite clear that we only have a part of the picture.
But I think that the permanent eradication of cancer is unlikely. I recognize this is not going to be a popular view, but it's a realistic view. My goal would be to reduce the incidence as much as we can, and I think it will be important that we manage cancer using agents that are the least toxic that we can use, and that will prolong life as long as possible.
Whether there are new drugs or old drugs, we still don't know how effective they will be. Will the metabolic approach run into the same limitations as the other cancer treatments?
We can't stay up on the surface of things, think that it will be simple, that cancer is a problem that we can solve with 3 or 4 drugs. We feel like we're advancing, and as we advance, it's like we're opening up a series of black boxes. We're bringing in some light, but then the light shows us that a little bit further on there's another black box. With this new idea, which emphasizes metabolism as an important factor, it is imperative that we not fall prey to the sort of oversimplification that could lead to the same kind of problems and disappointments that we had with the previous paradigms.
It will be important, though, to conduct the proper trials. And those trials will be large. They'll be much larger than the 3,600 patient study we're doing. They could include tens of thousands of individuals.
Why is it taking us so long to implement genuine wide-scale clinical trials for these drugs?
It is possible that the policies of the funding agencies over the last decades have encouraged, for example, gene-oriented research on cancer and have discouraged or slowed down other kinds of research. If somebody would have sent in a grant application on metabolism 20 years ago, they would have had a very hard time justifying why they wanted to work on metabolism.
The government has to almost, at least for the next 20 years, has to set up a special program for metabolism. And I'm being very serious about this because there are not enough people who can judge metabolism. And so, you know, you just have to say, we're going to put a certain amount of the budget, and the people who know metabolism will help us decide, and we're going to try to encourage other people to get into it.
But I'm afraid right now there is a lot of conservatism, and there's not enough money. And there are a lot of scientists out there, and they want papers, they want quick answers, and there is huge competition, and the kind of experiments we do takes a long time, and not very many people are as stubborn as I am. We need people to have the courage of their conviction.
It's crucial to continue taking an empirical approach. Look, we built boats long before we had any understanding of how boats are able to float and move. In the same way, we need to use empirical methods, that is, conduct clinical trials when dealing with cancer. And that's the work of physicians. We've had a lot of progress in treating cancer, even though we still don't really understand why. So through the empirical approach, huge advances have been made through the trials we've done, through our errors and observations. Hopefully this will continue, and as we acquire a better understanding of what is going on, our results will improve.
When the science is strong enough that the scientific community feels it is valid to test the benefits of these drugs, we need to make it easier for future studies to be initiated and for future investigators to get the funding that they need. And that's the challenge in this area. It's not a scientific challenge, it's a societal challenge.